Swayam Prabha. Digital India. Educated India.
Hello, in this lecture we are going to discuss the dynamics of impacting particles. The overview of this lecture is as follows. We will first define what is particle impact and classify different kinds of impact. Then we will look at the governing equations and the energetics of impact. What is impact? Impact is a short time impulsive interaction between particles. They are usually two particles or a particle and a rigid surface. There are various kinds of impact, but in this lecture we are going to restrict ourselves to impact of two particles. So, it is a short time impulsive interaction. That means, when the interaction takes place between the particles, there is an impulsive, there is a very short time impulsive force that acts between the on the particles. What could be the possible outcomes of such impact? You can have the two particles which were coming close and impacting, and then they can separate with energy conservation. The energy is not lost. Therefore, the final energy after impact and the energy before impact remains constant. Such impacts are called elastic impacts or elastic collisions. We can have separation, but some part of the energy might be lost. That means, the final energy can be less than the initial energy of the two particles. And we can have merger, which is called plastic impact. We will call it plastic impact. That means, two particles come together and they merge and become a single particle, or a single particle explodes to form multiple particles. Okay. In the short time scale of the impact process, the total linear or angular momentum of the system, the change is 0. The change in the total linear or angular momentum over that very short period when the impulsive force acts is 0. This we have seen in the previous lecture. We will make an assumption in all these analysis, and that is frictionless interaction. When the particles come close, they have a frictionless contact, and these particles were not interacting at finite separation. Now, we can have two kinds of impact or collisions, which are this direct central impact, where both the velocity of both particles, they are on the same line joining their centers, the particles, line joining the particles. Therefore, the velocity, the incoming velocity, that is on the line joining the particles. For example, this figure shows that. Oblique impact is, which is not direct central impact. Oblique means the particles might be moving in different velocity directions, suddenly there is impact and then there is separation. So, this is oblique impact. The velocities can be at the point of impact, the velocity directions will not be along the line joining the two particles. So, direct central impact, when the velocities are in the at the point of impact, the velocities are along the line joining the two particles, and oblique impact when they are not. We will start by analyzing elastic impact. Here I have shown in the figure two particles which come in with arbitrary velocities and they interact, they have a collision or impact and then they separate out. U is the initial velocity. So, for example, u1 is the initial velocity with which the particle, yellow particle comes in just before the impact. u2 is the initial velocity of the green particle just before the impact. v1 and v2 are the velocities after impact. Now, here I have additionally shown the normal direction and the tangential direction. The normal direction is along the line joining the two particles, and tangential direction is of course orthogonal to the normal. Now, there are two orthogonal directions. I have shown one, and the analysis that we will do, you will find that the behavior in the second orthogonal direction, orthogonal to the normal. So, the behavior in the second orthogonal direction is same as this tangential direction. So, you can have T1 and T2 as the two orthogonal directions to n. We will analyze only along T, but the behavior along the other tangential direction will be the same. These two things are satisfied for an elastic impact. First is the linear momentum conservation, and secondly the energy conservation. Let us look at the consequences of these two conservations. Linear momentum conservation, the total linear momentum of the system consists of these two particles. Total linear momentum of the system of these two particles before the collision is equal to the total linear momentum of these two particles after the collision, after the impact. m1 u1 vector plus m2 u2 vector must be equal to m1 v1 vector plus m2 v2 vector. This is linear momentum conservation. We also have energy conservation. The kinetic energy of the system before collision is half m1 u1 square plus half m2 u2 square. The kinetic energy of the system after the impact has taken place is half m1 v1 square plus half m2 v2 square. Now, what are the things given and what we have to solve? We are given the incoming velocities u1 and u2. Suppose we are given the incoming velocities, we have to find out the outgoing velocities. Of course, things can be differently posed. We are posing it for a moment, we are posing it in this form. How many conditions do we have? We have this vector condition of linear momentum conservation and a scalar energy conservation, the kinetic energy. Basically energy conservation here, because they are otherwise not interacting, only through there is no potential field, therefore, it is only kinetic energy. Had there been other potential fields, then you would have other potential energy functions. Okay, but as we have seen that these potential energy functions, these because they will not change as fast as in the short duration of the impact, during which the particles will hardly have the time to move. This was the central point of our discussion in the previous lecture. Therefore, the total energy conservation would be essentially the kinetic energy conservation just before and just after the impact. Now, we are given in this particular situation that we are going to analyze u1 and u2, the incoming velocities of the two particles. We have to determine v1 and v2. We have in this particular situation that I have drawn two velocity components along n and t, and therefore, we have 4 unknowns. v1 and v2 will have 2 components each. So, there are 4 scalar unknowns. There are, therefore, now we will have, with the linear momentum conservation, we have 2 scalar equations, and the kinetic energy has one scalar equation. Therefore, we have 3 scalar equations out of this one vector and one scalar equations. We have 2 equations from this and one equation from the energy conservation. In general, there will be 3 equations, but in that case right now there are 4 unknowns. If I assume that each velocity has only 2 components, then there are 4 unknowns. But if I consider the full 3 dimensional space, then there are 6 unknowns. Whatever situation you take, planar situation like this or spatial situation like this, the number of conditions are falling short as it looks, but we can find out the solution. Let us now look deep into these equations. In this particular situation, as I mentioned, I will reiterate, we are considering the planar collision problem, but the 3 dimensional full spatial collision problem, spatial impact problem can be analyzed in a similar manner. It does not make any difference. So, the considerations for the spatial problem will be the same. What do we do? So, we have the linear momentum conservation, 2 equations, and kinetic energy conservation, there is one scalar equation. Let us break or let us decompose the velocities. Now, if you look at the tangential, this is the free body diagram. I have drawn the free body diagram in which the forces have been shown in red. The velocities are not part of the free body diagram, but I have shown them for clarity of the understanding the situation. Impulsive force, because the contact is frictionless, impulsive force will act only at the common normal, only in the direction of the common normal. Here I have shown that Fi equal and opposite by Newton's third law acts along the common normal, which is the n cap direction. So, Fi acts along the n cap direction, and I have shown the incoming and outgoing tangential velocities of the particles, incoming and outgoing tangential components of velocities of the particles. This tangential components are being indicated by this superscript t. So, this is the for the first particle incoming velocity tangential, this is the for the first particle outgoing velocity tangential. Since we have considered frictionless contact, there is no tangential impact force. Therefore, the linear momentum in the tangential direction is conserved, which means that there is no change in linear momentum of the individual particles in the tangential direction. These particles are not subjected to any force in the tangential direction along the t cap direction. Therefore, for the individual particles, the tangential velocities are conserved. The incoming and outgoing tangential velocity components will be the same, and this has been written here. The change in the linear momentum of particle 1 in the tangential direction is 0. The change in linear momentum of the second particle in the tangential direction is 0, because there is no tangential force. What does this imply? This straight away gives us these 2 components which are equal. U1 in the tangential direction is equal to V1 in the tangential direction, and U2 in the tangential direction is equal to the V2 component in the tangential direction. So, we have for individual particles the linear momentum conservation in the tangential direction. Now, this if you just carry this problem to 3 dimension, this remains the same. Therefore, in the second tangential direction also these conditions will hold for the individual particles, Therefore, they straight away give you this velocity equality in both tangential directions for a spatial problem. We have scaled it down to a planar problem. Here we get these two conditions for the individual particles. Let us now look at the components of this linear momentum conservation equation in the two directions, normal and tangential. In the normal direction, how do I find out these components? I just take dot product of this full equation with n cap. If I do that, u1 vector dot n cap is u1 vector dot n cap is nothing but u1 in the normal direction. It is a scalar, it will give you a scalar, that is u1 component, the component of u1 in normal direction. Therefore, from the left hand side I get n1 u1 normal plus m2 u2 normal, and from the right hand side I get m1 v1 normal plus m2 v2 normal. I have taken a dot product with the normal direction. If I take dot product of that linear momentum conservation vector equation with the tangential direction t cap, then I get m1 u1 tangential plus m2 u2 tangential, incoming linear momentum of the system in the tangential direction is equal to m1 v1 tangential plus m2 v2 tangential. This is the outgoing linear momentum in the tangential direction. But just now we have seen that u1 in the tangential direction is equals to v1 in the tangential direction. What it means is this is equal to this and this is equal to this. The velocities in the tangential direction of the individual particles incoming and outgoing are same. So, this equation, this component, the tangential component of the linear momentum conservation is trivially satisfied. Had it been a spatial impact problem, this would have been the same situation when you take once with T1 and once with T2, the T1 cap and T2 cap, the two tangential vector directions. You will get trivially satisfied equations. Okay. Then we proceed. So, this is trivially satisfied. Therefore, what we are left with is the component of the linear momentum conservation relation in the normal direction of the system. Then we have the energy conservation. U1 square, remember U1 has these two components U1 and U2, U1 normal and tangential. This is u1, which is the incoming velocity of particle 1, has two components in the tangent and normal directions. Therefore, u1 square, note u1 square is u1 normal whole square plus u1 tangential whole square. Similarly, on the right hand side, the outgoing velocity of the particle 1 v1 square, which is the square of the or the magnitude square of the outgoing velocity magnitude of the square of the magnitude of the velocity of the outgoing velocity of the particle 1, you have v1 normal square plus v1 tangential square. Now, because the tangential velocity components of particle 1 incoming and outgoing are the same, which means this is the incoming tangential component of particle 1 is the outgoing tangential velocity component of particle 1, they are same. So, they will cancel from both sides. What I have written down, what happens after you have done all these cancellations, eliminations, and then you are left with half m 1 u 1 normal square plus half m 2 u 2 normal square is equals to half m 1 v 1 normal square plus half m 2 v 2 normal square. Therefore, I have used that condition that tangential velocity of individual particles remain the same before and after the impact. This is a scalar condition. In the just previous slide, we had this scalar linear momentum conservation of the system along the normal direction. Therefore, we have now two conditions. One is the linear momentum conservation equation of the system of two particles along the normal direction and the kinetic energy or energy conservation of the system. Both are scalar now, scalar conditions, and we have two scalar equations and we had two unknowns which we discussed. We are left with two unknowns. What are these two unknowns? Because our outgoing velocity, remember our outgoing velocity the outgoing velocities v 1 consists of v 1 normal and v 1 tangential, and v 2 consists of v 2 normal and v 2 tangential. Out of these four unknowns which we started off with, we have already found two of them. This is equal to the u 1 tangential which is specified, this is equal to u 2 tangential which is also specified. Therefore, we are left with these two unknown velocities. One is v 1 normal, the other is v 2 normal. These two are unknown, these two are the unknowns, and we have two scalar equations to solve for these two unknowns. Therefore, we should be able to do it. So, let me clear this clutter. Therefore, the complete formulation looks like this. I have now put all the relevant equations together and all the conditions that we have derived in one place. We have the linear momentum conservation of the whole system in the normal direction and the energy conservation, two scalar conditions, and these two are already found, they are known, right. These are the two conditions. So, you can now see that we have really four conditions, we get four conditions to solve for the four unknowns that we had, we started off with. Four scalar equations for four unknowns. These two are trivially solved because the initial velocity u 1 t and u 2 t, they are specified. Therefore, directly I can get v 1 t and v 2 t, and for v 1 n and v 2 n, the normal components, I have to solve these two equations, the linear momentum conservation in normal direction and the kinetic energy conservation of the system. Now, we will discuss inelastic impact. Linear momentum conservation is always satisfied. Remember what is inelastic impact, in which you have energy, you do not have energy conservation, but linear momentum conservation is always there. If you follow the same steps as we have discussed for the elastic impact, then except the energy conservation, everything else remains the same, and those three conditions I have written down. But remember that we started off with 4 unknowns, 2 of them are trivially solved by the 2 conditions here, last 2 conditions. We are left with therefore 2 unknowns, the normal components V1 n and V2 n, but we now have only the linear momentum conservation of the system in the normal direction. We do not have the energy equation, energy is not conserved. What people do is to study something called restitution, the deformation and restitution process during impact, and a coefficient of restitution is defined. How is it defined? The coefficient of restitution is the impulse of the force during restitution divided by the impulse of the force during deformation. Now, what are these processes? Imagine 2 particles which are coming in and impacting. Once they start that impact and they are deforming, they are coming closer and closer, that is called deformation process. When you have this deformation process, then the force acting between the 2 particles, equal and opposite of course by Newton's third law, is denoted by Fd. The force that acts on the 2 particles is Fd during the deformation process. At a certain point around midway, now the deformation stops and the particles now will start relaxing or they will start separating. This is called the restitution phase. During restitution phase, the force that acts between the particles is denoted by Fr. Now, you can calculate the impulse of these 2 forces in the individual time intervals. For example, here the deformation impulse is calculated from when impact starts at t equal to 0 and goes up to t prime, and during this time interval the force that acts between the 2 particles is Fd. Therefore, the deformation impulse during deformation is integral from 0 to t prime is Fd dt. Similarly, now from t prime to t, when the particles have started separating out, it is called the restitution phase. There the force between the 2 particles is Fr. Therefore, the impulse during the restitution phase is from t prime to the total time of contact. T is the total time of contact. So, from t prime to t, if you calculate the impulse of the restitution force, then it is that integral in the numerator, and this ratio is called the coefficient of restitution, and that can be shown to be equal to this quantity, the mod value of V2 minus V1. V2 minus V1 is the relative velocity of 2 relative to 1. This is the relative velocity V2 relative to 1. This dot the n cap, the normal vector, unit normal vector, that sits in the numerator. So, this is the outgoing velocity. V2 is the outgoing velocity of particle 2 minus V1 is the outgoing velocity of particle 1. In the denominator sets u2 minus u1, which is u2 relative to 1, this vector dot n cap, and mod value is taken. This is nothing but the velocity of the relative velocity of separation divided by relative velocity of approach. relative velocity of separation by relative velocity of approach. And remember, we have to take the mod value, that means E is a positive quantity. V2 normal minus V1 normal by U1 normal minus U2 normal. Now, this is to take care of the sign that this is positive. So, relative velocity, separation velocity by relative approach velocity. So, we have this concept of coefficient of restitution, and this is determined experimentally. The coefficient of restitution is determined experimentally. It can depend on various factors. Therefore, this is a matter of research. The coefficient of restitution has to be determined for different kinds of surfaces, different curvatures, etc. This has to be determined experimentally. For elastic collision, the coefficient of restitution is 1, and you can check that energy is conserved. In elastic collision, we have E lying between 0 and 1. It is not equal to 1, it is not equal to 0, but lies between 0 and 1. For plastic collision, where there is merger, E is 0, which means there is no separation, right? There is no separation. There can be an approach velocity, but there is no separation. Now, when you have plastic impact, linear momentum is conserved. Now, you can have merger or explosion. Therefore, for merger, you have the linear momentum conservation reads as m1 incoming velocity of particle 1 plus m2 incoming velocity of particle 2 must be equal to m1 plus m2, the final velocity of the total mass, right, the combined body. And you can calculate the energy that is lost by calculating the final energy, which is half m1 plus m2 v square minus half m1 u1 square plus half m2 u2 square. So, by calculating the difference in the energy, you can calculate the energy lost. For explosion, you have, I mean, the initial body was a single piece, and you have two pieces generating out of their suppose two pieces, then m1 and m2. So, initial body was having mass m1 plus m2, initial velocity was u, let us say, and final velocities of these two pieces is v1 and v2, then linear momentum conservation is as shown. And why explosion takes place? Somewhere energy has to be released. So, energy release, so it could be chemical energy or something. You can, from this information, what was the initial, what was the final kinetic energy and what was the initial kinetic energy, from this you can find out what was the amount of energy that was released during collision. Okay, to summarize, we have looked at short time impulsive interaction between two particles. We have classified them as elastic, inelastic and plastic impact, and we have used the fact that short time change in the total linear momentum, or we have not talked about angular momentum, we will talk about it very soon, but the total linear and angular momentum of the system, the change in this total linear or angular momentum of the system in this very short duration is 0, and we have assumed frictionless interaction. So, with that I will close this lecture.